Welcome to a lesson on definite integration of vectored valued functions. To determine the definite integral of a vectored valued function, we integrate each component separately. So looking at our first example, because the vectored valued function only has an x and y component, we'll have two definite integrals. This is equal to the definite integral from 0 to 2 of e raised to the power of 4t dt times I minus the definite integral from 0 to 2. Instead of the square root, we'll use the 1/2 power. So we'll have the quantity t plus 1 to the 1/2 dt times j. And now we'll integrate. Looking at this first integral, notice how we'll have to use u substitution, where u is equal to 4t, and differential u is equal to 4 dt. So if we divide both sides by 4, if we write this as e to the u, we'll have an extra factor of 1/4, which means the antiderivative is 1/4 e to the 4t. But remember, this is definite integration, so we have our limits of integration from 0 to 2 times I, and then minus. This may appear it requires u substitution, but notice the inner function is u equals t plus 1, therefore differential u is dt. So we can use the basic power rule here. So we'll add 1 to the exponent and then divide by that new exponent. 1/2 plus 1 is 3/2. And then instead of dividing by 3/2, we'll multiply by the reciprocal. So we'll have 2/3 times the quantity t plus 1 to the 3/2 power, again from 0 to 2, times j. Now we'll evaluate. We'll first substitute 2 for t. So we'll have 1/4 e to the 8th, 4 times 2 is 8, minus 1/4 e to the 0 times I. And then here we'll have 2/3. When t is 2, we'll have times 3 to the 3/2, and then minus 2/3 times 1 to the 3/2 times j. Let's go ahead and factor out 1/4 here. E to the 0 is equal to 1, so we'll have 1/4 times e to the 8th minus 1 times I, and then minus, here we'll factor out 2/3, leaving us with 3 to the 3/2 minus 1 times j. Now let's take a look at a second example. Notice how the vectored value function has an x, y, and z component, so now we'll have three definite integrals. Now when we integrate, notice how here we have to perform u substitution, where we'll let u equal sine t. Therefore, differential u is equal to cosine t dt, which is a perfect fit. We can write this in terms of u as the integral of u squared, and then because cosine t dt is equal to du, this is just du, which means the antiderivative in terms of t would just be u to the 3rd divided by 3, or sine cubed t divided by 3. And now for the next integral, notice that u is equal to cosine t this time, because this is raised to the 2nd power. So differential u is equal to negative sine t dt, which means negative du is equal to sine t dt. So in terms of u, this would be negative u squared du. Again, sine t dt is equal to negative du, giving us this negative. And then for the antiderivative in terms of u, we'll have negative u to the 3rd divided by 3, which would be in terms of t minus cosine cubed t divided by 3. And then finally the integral of 2 with respect to t would be 2t, so we have 2t times k. So we first substitute t equals pi over 2. Sine pi over 2 is 1, so we'll have 1 cubed divided by 3, that's 1/3, minus, when t is 0, sine 0 is 0, so it'll be minus 0, times I, minus, cosine of pi over 2 is 0, so we'd have 0 minus, cosine 0 is 1, so we'd have 1 cubed divided by 3, or 1/3, times j, and then plus, notice when t is pi over 2, we have 2 times pi over 2, which is just pi, and then when t is 0, it's minus 0 times k. So we're left with 1/3 I. This is minus negative 1/3 j, or plus 1/3 j, and then plus pi k. Okay, I hope you found this explanation helpful.